Hello and welcome to today's lesson. We'll be talking about gas stoichiometry, Dalton's Law of partial pressures, kinetic molecular theory of gases, diffusion, effusion, and some other characteristics about real gases. So that's what's on the agenda today. Sorry for the delay. It took me a little bit to get the PowerPoint up. So we'll start off with a basic stoichiometry problem involving gases. So whenever you're doing stoichiometry with gases, somewhere in the problem, either at the beginning or the end, we're going to be using the ideal gas equation. So in this problem here, we have solid lithium hydroxide used to scrub CO2 from spacecraft. The CO2 reacts with the lithium hydroxide to produce lithium carbonate and water. What mass of lithium hydroxide is required to remove? So we're looking for the mass of lithium hydroxide to remove 215 liters of CO2 at 23 degrees Celsius and 0.942 atmospheres. So again, what we're looking for, mass of lithium hydroxide, that's what we are looking for. Now with stoichiometry, we always need to start with a balanced chemical equation. So here we're starting with lithium hydroxide plus CO2 gives us lithium carbonate plus water. Anytime you do stoichiometry, you have to have a balanced chemical equation. So let's check this space. 3 oxygen, 4 oxygen, 2 lithium. You need a 2 here. So we have 2 hydrogen, 4 oxygen, 1 carbon, and 1 carbon. So this is our balanced chemical equation. And so now we need to somehow get mass. And when we use stoichiometry, the way we find mass is if we know the moles of lithium hydroxide. But we don't know the moles of lithium hydroxide. But using stoichiometry, if we found the moles of CO2, we could find the moles of lithium hydroxide, because here we'll see that for every 2 moles of lithium hydroxide, we need 1 mole of CO2. So if we know the moles of carbon dioxide, we can determine the moles of lithium hydroxide and then determine the mass. So now in order to determine the moles of CO2, we have to look at the other information given to us. We know the volume of CO2. We know the temperature of the CO2 collected at. And we know the pressure of the CO2. So what we have here is we have pressure of CO2, and it's already in atmospheres, which is good because we don't have to convert. We have the temperature, which is 23 degrees Celsius. So we need to convert that to Kelvin, which would be 296. And we have the volume of gas collected. It's already in liters, 215 liters. So now we can use the ideal gas equation PV equals nRT, where R is the gas constant. And we can rearrange this to solve for moles. So moles equals PV divided by RT. So if we know the pressure, the volume, and temperature, we can calculate the moles of carbon dioxide. Then when we know the moles of carbon dioxide, we can determine the moles of lithium hydroxide. So moles equals P times V divided by R times T. And again, this will be the moles of CO2. So we have 0.942. Divided. So I get 8.33 moles of CO2. Now that we know the moles of CO2, we can find the moles of LiOH, lithium hydroxide, using the mole to mole ratio. So we have 8.33 moles CO2 times, for every 2 moles of lithium hydroxide, there is 1 mole of CO2 needed. And this will give us the moles of lithium hydroxide, 16.67 of lithium hydroxide. Now that we know the moles of lithium hydroxide, we can find the mass. So moles times molar mass equals mass. So 16.67 moles times so mass times molar mass will give us, excuse me, moles times molar mass will give us mass. And so it's 400 grams of lithium hydroxide. So that's how much lithium hydroxide is needed to remove 215 liters of CO2 at 23 degrees Celsius and a pressure of 0.942 atmospheres. So I'll give you a moment to look over that before I clear the page. Next, we're going to talk about another law of involving gases, which is Dalton's law. So with mixtures of gases, as we said earlier in this chapter, gases mix homogeneously, meaning they form solutions. So you can't determine where the individual components are. And each gas behaves as if it were the only gas present. So if you know the gas of each, if you know the pressure of each gas in your mixture, you can determine the pressure of the mixture of gases. And so the pressure that is exerted by one type of gas in a mixture is called the partial pressure. So for example, if we have a mixture of air, and you see O2 has a partial pressure of 20.9 kilopascals, into 78.1 kilopascals, argon 0.97, etc. Since we know the individual or the partial pressures of each component in air, when we add them up, we get the partial pressure, or excuse me, we get the total pressure of the mixture, which is 101.3 kilopascals. And so this law that describes this is called Dalton's Law of Partial Pressures. So to get the total pressure of the mixture, you have to add up the individual pressures of each gas in the mixture. So the P total is the sum of the partial pressures of the individual gases. Now, another thing we can gather from this is something called mole fraction. So mole fraction is simply taking the fraction of moles of one of your components in the mixture and dividing it by the total moles of the component. And so mole fractions should always be less than 1. With Dalton's law, one type of property we get is the mole fraction. Also, we can determine the partial pressure of a gas if we know the mole fraction of that component in the mixture, and we know the total pressure of the mixture. We can determine the partial pressure of the gas. Now, in some reactions, they specify that the gas was collected over water. So when the gas is collected over water, the total pressure is the pressure of what we refer to as the wet gas. So again, when a gas is collected over water, this is referred to as a wet gas. And so a wet gas includes the pressure of the gas, which we call the dry gas, and the pressure, the vapor pressure of water. So that's the individual components add up to the whole. So whenever you're collecting a gas of water, you have to subtract out the vapor pressure of water to get the actual pressure of the gas. So here we have an example of a problem involving Dalton's law of partial pressure. So we have 0.6 liters of argon at 1.2 atmospheres, 227 degrees Celsius, and we mix it with 0.2 liters of O2 at a 501 torr and 127 degrees Celsius. So we have these two individual gases at different pressure, volume, and temperatures, and we add them to a 400 ml flask at 23 degrees Celsius. What is the pressure of the flask? So again, the pressure of the flask, P, when we're looking at for P total would equal total moles times R times T divided by V. So V is given to us 400 milliliters, which we convert to liters. T is given to us 23 degrees Celsius. Which we convert to Kelvin, 296 Kelvin. The only thing we're missing is the total moles of gas in the mixture. So once we find that, we can determine the total pressure of the mixture. Now remember, in total equals the moles of argon plus the moles of O2. So in order to find the moles of argon and the moles of O2, we're going to have to use this other information given to us. So this 0.6 liters, 1.2 atmospheres, 227 degrees Celsius. That's the conditions of argon. From that, we're going to determine the moles of argon. And we do the same thing with the 0.2 liters at 501 torr and 127 degrees Celsius. So we're going to use that information to determine the moles of argon and the moles of O2. So for argon, volume is 0.600 liters, pressure 1.2 atmospheres. Both of those are in the correct units. Temperature 227 degrees Celsius. It's 500 Kelvin. Now that we know this, we can calculate the moles of argon. Get 0.0175. Now for oxygen, we do the same thing. So the volume of oxygen, 0.200 liters. The pressure is 501 torr. But for the pressure, we got to convert it to atmospheres because our R is in atmospheres. So we divide by 760, we get ATM. And then we have the temperature, 27 degrees C, which is 300 Kelvin. Now we can calculate the moles of O2. So we get 0.2053. Just double check. Okay. Now we can find the total moles. Point 0.0175 plus get 0.02285 moles. Now we know the total moles, we can find P total. So we get a pressure of 1.39 ATM. So that's the pressure of the mixture of these two gases. I'll give you just a moment to look at that before we move on to another example. Here we have a stoichiometry problem. So we want to know how many liters of hydrogen gas are collected over water at 18 degrees Celsius and 725 millimeters of mercury when 0.84 grams of lithium hydroxide reacts with water. Aqueous lithium hydroxide also formed. And it gives us the vapor pressure of water. This is at 18 degrees Celsius. Because it's collected over water, it has to give us the vapor pressure of water. So the first thing we always need is a balanced chemical equation. So when we want lithium reacts with water, so lithium plus water gives us hydrogen gas plus aqueous lithium hydroxide. So we have one oxygen, we have 3 hydrogen, 2 hydrogen. We got to put a 2 here. That's 4 hydrogen and 2 oxygen. We put a 2 here, and we put a 2 here. So this should be a balanced chemical equation. So what we're looking for in this is the volume of H2. What we know is the temperature at which this gas was collected at 18 degrees Celsius. Convert that to Kelvin. 291 Kelvin. The pressure of the gas, we know that. But by the way, this pressure is the pressure of the wet gas. Because remember, it was collected over water. So to get the pressure of H2, we have to subtract the vapor pressure of water from the pressure of the wet gas. And it's best to do this in millimeters of mercury. That way, less chance for you to have an error. Should be 709.5 millimeters of mercury. And then we can convert this to ATM. So divide by 760. 0.9336. It's always good when you're converting to ATM to keep 3 or 4 significant figures, because if you round too much, because of significant deviation in your answer. So in order to calculate the volume of H2, volume equals nRT divided by P. So the only thing we're missing are the moles of H2. So we have to use the other information to find the moles of H2. And what do we know? We know that there was 0.84 grams of lithium that reacted, and we know for every 2 moles of lithium, we form 1 mole of H2. So what we can do is we can take the mass of lithium and convert it into moles of lithium. So where moles equals mass divided by the molar mass. Point. And this is the moles of lithium. Then we can take this and multiply it by the mole ratio, which is 1 mole of H2 for every 2 moles of Li. Now that we know the moles of H2, we can determine the pressure of H2, or excuse me, the volume of H2. So volume equals so we get 1.55 liters. So that's the volume of H2. Again, the important thing is to remember to subtract out the vapor pressure of water from the total pressure of the mixture. That way you only get the pressure of hydrogen gas. You need a few seconds to kind of let that sink in. So now we're going to talk more about the characteristics of how gases behave. And what we like to talk about is the kinetic molecular theory model for gases. This kind of describes how gases behave. And since we're dealing with ideal gases, we have certain assumptions that we do. So there are 3 things that describe how gas particles behave, and that's the particle volume, the way it moves, and how the gas molecules collide. So for an ideal gas, we assume that the volume of the actual gas particle is small compared to the whole sample. So if you have a gas in a container, the actual space that the molecule takes up is very small compared to the total volume of the container. So we assume that the molecule doesn't take up any volume. So the volume of the container equals the volume of gas. For particle motion, we assume that the gas molecules are always moving in constant, random, straight line motion. And the only time they change is when they collide with either the wall, which produces pressure, or each other. For particle collisions, these are elastic, so they just bounce off each other. I guess, again, according to we assume ideal gas behavior. This is important. The total kinetic energy is constant at a given temperature. So all gases at a given temperature have the same kinetic energy. And molecules are not influenced by attractive or repulsive forces between each other. So there's no interaction between the molecules. And so these 3 postulates make up the kinetic molecular theory model for gases, or called KMT model for gases. That's out of sync. Let me fix this. Sorry about that. So when we talk about gases, we need to talk about the speed of gases. And what we refer to mostly is the most probable speed. And the most probable speed is generally the apex of the curve you see here, of each line in the curve. And so this is the most probable speed shown here. And so what we should notice is that this most probable speed increases as temperature increases. So as you increase the temperature, you see that the most probable speed shifts to higher speeds. So as you increase the temperature, you increase its most probable speed. And you also notice that there's more of a broadening of the curve. There's molecules are moving at a more variety of speeds at higher temperature versus lower temperature. But the thing to remember is that at any temperature, all gases have the same average kinetic energy. So if all gases at 300 Kelvin have the same kinetic energy, all gases at 600 Kelvin, same kinetic energy. So at a given temperature, all gases have the same average kinetic energy. Now, the energy associated with motion is kinetic energy, and as you see here, kinetic energy is related to the mass and the velocity. And at a given temperature, you see that the heavier the gas, such as O2, which has a molar mass of 32, versus a lighter gas, such as H2, which has a molar mass of 2, the lighter the gas, the faster the most probable speed is. The heavier the gas, the slower the speed is. We're going to explain why this is in just a moment. So from the molecular mass, you can get some kind of information on, when you're comparing different gases, which one would have the fastest or slowest, most probable speed at a given temperature. So as you go to lighter gases, they move faster. And the reason this is because at a given temperature, again, kinetic energy of a heavier object and the kinetic energy of a lighter object have to be the same. And so since kinetic energy is mass and velocity, those two components are involved in kinetic energy. For a heavier object, it moves slower so that it has the same kinetic energy as a lighter object that moves faster. The way we measure the average kinetic energy of particles is through temperature. So as you increase the temperature, you're going to increase the kinetic energy of that gas. And so we're not going to do any actual calculations involving the speed of a particle, but just to show you that the speed of a particle of gas or a gas molecule is directly related to the temperature and inversely related to its molar mass. So this is referred to as root mean squared speed. So again, the speed of the gas is directly related to its temperature, inversely related to its molar mass. And again, this has the molar mass. You know, if they have a lighter object, it has a smaller molar mass, it has to move faster so that it has the same kinetic energy of a heavier object that has a greater molar mass, which moves slower. So how do gas particles move? One type of way is referred to as effusion. So effusion is the movement of gas molecules through a tiny hole. So you have a tiny hole, gas molecules move through there. That is referred to as effusion. And so a law that describes how effusion behaves is called Graham's law. So Graham's law says the rate of effusion is proportional to the inverse of the molar mass. So what does this mean? This means that the heavier the gas is, the slower it effuses. And so if we know the gas, the rate of one gas and the rate of a second gas, we can determine one of their molar masses. Or if we know the molar mass of each gas and we know the rate of one gas, we can calculate the rate of the second gas. And notice that for rate A, molar mass of A is on the bottom. For rate B, which is on the bottom here, molar mass of B is on top. Because remember, rate and molar mass are inversely related. And so we can use this to determine the identity of an unknown gas. So if we know the rate of an unknown gas and we know the rate of a known gas, we can determine the molar mass of our unknown gas and then possibly the identity of the gas. We'll look at a problem of that in just a moment. Another type of movement of gas is diffusion. And so diffusion is just the movement of gases, the mixing of gases. So if you let a particular gas out at one end of the room and another gas out at the other end of the room, they're going to diffuse until they're thoroughly mixed with one another. So Graham's law of effusion also works for diffusion. And again, the rate of diffusion is inversely related to the molar mass of gas. So the heavier the gas, the slower it diffuses. And just to let you know, a side note, diffusion rates are a lot lower than effusion rates. So here we have a problem involving effusion. So at a given pressure and temperature, it takes 4.85 minutes for 1.5 liters of a sample of helium to effuse through a membrane. How long does it take 1.5 liters of fluorine to effuse under the same conditions? So just a few notes here. It's given us time. And so rate is actually 1 divided by the time. So remember, if it gives you the time, 1 divided by the time gives you the rate. Secondly, F2 is heavier than helium. Therefore, the time it takes should be longer. So our answer should be greater than 4.85 minutes. So let's go through this. So we're going to set up using Graham's law. So again, 1 divided by the time gives us the rate of helium. We don't know the rate of F2, and then we're going to set that equal to the molar mass of F2 and helium. So we find the molar masses of each of our gases, and we solve for the rate of F2. Again, this is the rate. To find the time, we take the inverse. So time is equal to 1 over the rate. So I forgot to do that, so let's do that. So time is equal to 1 divided by 14.9. So that's the rate. I think I did something wrong here. Let me see. 0.2062 divided by 0.0669. So this is actually incorrect. Let's scratch this out. I made a boo-boo here. So rate of F2 equals 0.2062 divided by 3.08. and we get 0.06695. So that's the rate of F2. Now remember that time is equal to the inverse of the rate. So the time, or T, for F2 would be 1 divided by 0.06695. Which would be 14.9 seconds. So actually, this is not the rate of F2. It's actually the time for F2. So again, always make sure that when you're given time, 1 divided by time is the rate. Again, this is not seconds. Made another typo. This is minutes. Give you a second to look over that and notice that the time it takes is longer for fluorine than for helium. Look at one more problem. We have a sample of neon gas. It infuses in a container in 76 seconds. The same amount of an unknown noble gas requires 155 seconds. What is the identity of the gas? So in order to get the identity of the gas, we're going to need the molar mass of the unknown gas. Once we know the molar mass, we know the unknown gas. So again, we're going to be using Graham's law. So the rate of X, which is our unknown gas, divided by the rate of neon equals the molar mass of neon divided by the molar mass of X raised to the 1/2. So remember, rate is 1 over time. So rate of X is 1 divided by 155. And notice that for, let me do this first, and then we'll talk about that. 0.0. Notice that the rate of the unknown gas is longer than the rate of the neon gas, which tells you that the unknown gas is going to be heavier than neon. So the rate of neon and divided by 76. Now we know the rate of each, the molar mass of neon, is 20.18. Now we can set up Graham's law and solve for the molar mass of our unknown gas. Work through the math. The molar mass of our unknown gas is 84.5 grams per mole. And we look this up on the periodic table. We see that the closest noble gas to that is krypton. So our unknown gas is krypton. Give me a few seconds to look over that before we move on to real gases. We're just going to touch a little bit on real gases and how they deviate from ideal gas behavior. Just a little bit. I mean, we're not going to do any calculations with real gases. Real gases actually use a different equation called van der Waals equation to calculate the pressure and volume. We're not going to cover that in this class, but if you take a biophysical class or a physical chemistry class, you may use van der Waals equation. And it accounts for the behavior of real gases. So there are two deviations that real gases do compared to ideal gases. First off, the gas particles are not point masses. The volumes of the gases are determined on the size of their atoms. So the actual volume of the gas is a little bit smaller than the volume of the container because the molecules occupy some of that volume. So that's one deviation from ideal gas behavior. The second one deals with attractive and repulsive forces. So this affects the pressure. If molecules are attractive, it means it kind of causes the pressure to decrease. If they're repulsive, increases the pressure. And this is due to the types of subatomic particles and the polarity of the gases. So those are two ways that real gases deviate from ideal gas behavior. Now, as regards to temperature and pressure, ideal behavior of a gas deviates when you're at low temperature and high pressure. So if your gas, if you change the pressure and you decrease it, it's going to have less ideal gas behavior at the lower temperature. If you have a gas and you increase its pressure, it's going to deviate more from ideal gas behavior. And in general, the closer the gas is to the boiling point, the more it's going to deviate from ideal gas behavior. So in this first graph, we have gases at high pressures, and this little black dotted line represents an ideal gas. And you see that all these gases deviate significantly from ideal gases. And again, this is at high pressure. Whereas at low pressure, most of the gases follow ideal gas behaviors. So an ideal gas prefers low pressure and high temperature. So again, let's write that down. Ideal gas prefers low pressure, high temperature. So if you want to make something behave as an ideal gas, it prefers low pressure, high temperature. Because what happens is at low pressure, the gas molecules are very far apart. But when you increase the pressure, the gas molecules get closer together. And now, remember, as pressure increases, volume decreases, the gas molecules get closer together. There's more attractive repulsive forces between them. And there is more of the volume of the gas accounts for the volume of the container. So here are just two examples involving real gases, whether or not it behaves more ideally or less. So here we have nitrogen gas. We want to know, will it behave more ideally at 1 atm or 500 atm? Now, to behave more ideally, remember it prefers low pressure. So the answer would be 1 atm. Now we go to the second example. It tells us the boiling point of sulfur hexafluoride is 16 degrees Celsius. Would it behave more ideally at 150 degrees Celsius or 20 degrees Celsius? And the answer is 150 degrees Celsius because it's a higher temperature further from the boiling point. So the higher the temperature, the more ideal the gas behaves. And so this brings us to an end to chapter 5. And so from chapter 5, we learned about the individual gas laws. We learned about ideal gases and ideal gas equation, deviation from or other types of derivations of the ideal gas law, so we can calculate the molar mass of the gas or the density of the gas using the ideal gas equation. We talked about gas stoichiometry. We talked about Dalton's law of partial pressures, kinetic molecular theory of gases, effusion, diffusion, and real gases. So the next lecture will be over energy and calorimetry, which is chapter 6. I hope you enjoyed the video. Please leave a comment if you like it. So on that note, see you next time.